On the 14th of September 2015, at 9:50 in the morning Coordinated Universal Time, two machines on opposite sides of the United States registered something that had never been detected before. They registered a change in the length of their arms. Not a large change, not a visible one. It measured approximately 1,000th of the diameter of an atomic nucleus across an arm 4 kilometers long. And yet the instruments found it. They had been designed over half a century of physics and engineering to find exactly this kind of signal in exactly this kind of noise. On that morning, they succeeded for the first time in human history. The detector in Livingston, Louisiana, registered the disturbance first. 7 milliseconds later, the detector in Hanford, Washington, registered the same signal. The signal lasted 0.2 seconds in the sensitive frequency band of the detectors. In that fraction of a second, its frequency swept upward from about 35 Hz to approximately 150 Hz. Converted to audio and played at normal speed, it sounds like a brief upward chirp, a soft rising tone that lasts less than a quarter of a second. Scientists in the collaboration call it the chirp. It is the gravitational cry of two black holes, each more massive than 30 suns, completing their final orbit and becoming one. The person who first saw the signal was a postdoctoral researcher named Marco Drago at the Albert Einstein Institute in Hanover, Germany. He was monitoring the detection pipeline when the alert arrived at 5:51 in the morning local time. The signal was so clean, so unmistakably the shape a black hole merger should produce according to Einstein's equations, that his first reaction was suspicion. The LIGO collaboration routinely inserted synthetic signals into the data to test the pipeline. These were called blind injections. Drago's first thought was that this was one of those tests. He sent an email asking whether anyone had authorized a blind injection. The answer was no. The machine had found something real. 5 months of analysis followed. Over 1,000 scientists from nearly 100 institutions checked every conceivable alternative explanation. Vibrations, seismic tremors, electromagnetic interference, instrumental glitches. Each was tested and eliminated. The signal was consistent with the merger of two black holes of approximately 36 and 29 solar masses, located about 1,300,000,000 light-years away. The merged remnant was approximately 62 solar masses. 3 solar masses had been converted entirely into gravitational wave energy in less than 1 second. On the 11th of February 2016, the LIGO collaboration announced their discovery. The Nobel Prize in Physics followed in 2017. The ripple had been traveling for 1,300,000,000 years. It started in a distant galaxy before the Earth existed. While complex life was just appearing on Earth, those two black holes were still more than 1 billion years from their final collision. While the dinosaurs lived and vanished, they were still circling. The ripple departed its source, crossed 1 billion galaxies, and arrived at our two instruments at the exact moment in human history when we had finally built something sensitive enough to feel it. Had LIGO gone online a decade earlier, before the advanced LIGO upgrades were completed, the signal would have passed through undetected. The timing was, by any honest assessment, extraordinary. This documentary follows the complete story of that event and every event like it. We will begin with what a black hole actually is. Not the popular image, but the precise physics. Then we will follow the long journey of two black holes finding each other in a binary star system, spiraling inward across billions of years, and finally colliding in the most energetic event the universe produces. We will explore what gravitational waves are and how LIGO was built to detect them. We will examine what happens when supermassive black holes at the centers of galaxies merge, and we will look forward to what the universe becomes as black hole mergers accumulate across cosmic time. The full story. Settle in. There is a quality to this particular discovery that I find different from other scientific milestones. The detection of a gravitational wave is not like seeing a new planet or measuring a new particle. It is the opening of a fundamentally new channel of perception, a sense that humanity did not have before September 14, 2015. The universe has been making gravitational waves continuously since the first massive stars died and the first black holes formed. For all of human history until that morning, we had no way of perceiving them. We were deaf to an entire category of cosmic event. Then the instruments came online, and the universe began to speak to us in a language we had never heard. And the first word it spoke was a chirp. The LIGO detectors did not operate alone. The International Network of Gravitational Wave Observatories, LIGO in Louisiana and Washington, Virgo in Italy, Kagra in Japan, operates as a single scientific instrument distributed across the Earth. When a gravitational wave passes through, the signal arrives at each detector at a slightly different time, depending on the source direction. By comparing arrival times and the shape of the signal at each site, astronomers can triangulate the source position on the sky and determine the orientation of the binary's orbital plane. The network is also essential for distinguishing genuine gravitational wave signals from local disturbances. A truck driving past the Livingston site can shake the detector. The same truck does not shake the detector in Hanford. Only a gravitational wave, traveling at the speed of light, produces a correlated signal in both detectors within the expected time window. This coincidence requirement is one of the most powerful tools in rejecting false positives. The phrase black hole is one of the most familiar terms in popular science. And yet when pressed to explain precisely what one is, most people find the words becoming difficult. They know it is dark. They know things fall in. They know light cannot escape. But the physics behind those facts, the geometry of space and time that makes a black hole what it is less commonly understood. That is what this chapter builds, piece by piece, at the pace of a quiet conversation. The concept is genuinely strange, but it is also genuinely beautiful, and the strangeness yields completely to careful thinking. We begin with escape velocity. If you throw a ball upward on Earth, it rises, slows, and falls back. You did not give it enough energy to escape Earth's gravity permanently. But throw it at 11.2 kilometers per second, and it escapes completely. It will travel outward forever, without any further propulsion. This minimum speed needed to permanently escape a body's gravitational pull is called escape velocity. The Moon's is lower than Earth's. The Sun's is about 617 kilometers per second. Escape velocity increases as the object becomes more massive or more compact at the same mass. Now take that logic to its extreme. Imagine compressing the Sun while keeping all its mass the same. As its radius shrinks, the surface gravity rises, and so does the escape velocity from that surface. At a critical radius, the Schwarzschild radius, named for physicist Carl Schwarzschild, who derived it in 1916, the escape velocity from the surface reaches the speed of light. At that point, nothing can escape, because nothing travels faster than light. The region inside that critical radius is, by definition, a black hole. For an object with the Sun's mass, that radius is approximately 2.95 kilometers. The entire mass of the Sun compressed into less than 3 kilometers in radius. The surface defined by the Schwarzschild radius is called the event horizon. It is not a physical boundary you could press your hand against. It is a mathematical surface, a point of no return in the causal structure of spacetime. If you were falling into a sufficiently large black hole, you would feel nothing unusual at the moment you crossed the horizon. The tidal forces at that surface scale inversely with the square of the mass, meaning for a supermassive black hole, crossing the horizon is unremarkable. For a stellar mass black hole, the tidal forces at the horizon would be enormous. But once you cross, in either case, no signal you send can reach the outside universe. You are causally disconnected from everything behind you. At the center of a non-rotating black hole is the singularity, the point where the density becomes mathematically infinite and the equations of general relativity break down. The singularity is not a place in the ordinary sense. Inside the event horizon, the singularity is better understood as a moment in time, not a location in space. All trajectories inside the horizon lead inevitably toward it, the way all paths through time lead toward tomorrow. This is one of the most counterintuitive aspects of black hole geometry. Inside the horizon, space and time exchange roles. The singularity is when, not where. General relativity predicts it but cannot describe it. A complete quantum theory of gravity is needed there, one we do not yet have. Real black holes in nature are not non-rotating, they spin. When a massive rotating star collapses to form a black hole, it retains its angular momentum. The resulting spinning black hole is described by the Kerr solution, derived by New Zealand physicist Roy Kerr in 1963. A Kerr black hole has an additional region outside the event horizon called the ergosphere, a zone where space-time itself is dragged around by the rotation, a phenomenon called frame dragging. Inside the ergosphere, it is impossible to remain stationary relative to distant stars. The spin of the final black hole in a merger affects both the gravitational wave signal and the efficiency with which the merged object eventually settles into its final state. There are 4 known classes of black hole by mass. Stellar mass black holes form from collapsed massive stars and range from a few to roughly 100 solar masses. Intermediate mass black holes from a few hundred to 100,000 solar masses likely form through runaway stellar mergers in dense star clusters or through hierarchical black hole mergers. The topic of Chapter 8. Supermassive black holes at the centers of large galaxies range from 1 million to tens of billions of solar masses and are the subject of Chapter 7. And primordial black holes, a theoretical class that may have formed directly from density fluctuations in the very early universe, could potentially have masses ranging from less than a gram to millions of solar masses, depending on the epoch in which they formed. Between the event horizon and the singularity sits a region called the photon sphere, at 1.5 times the Schwarzschild radius for a non-rotating black hole. This is where a photon of light can orbit in an unstable circular path. It is photons captured near this surface that produce the bright ring visible in the Event Horizon Telescope image of Messier 87 star, released in 2019. The first direct image of a black hole's immediate environment. That luminous ring is light bent into near-circular orbits by extreme gravity, photons that have looped around the black hole 1 or more times before escaping toward us. A common misconception is that black holes are cosmic vacuum cleaners that suck in everything around them. They are not. A black hole exerts the same gravitational pull as any other object of the same mass at the same distance. If the Sun were replaced by a black hole of equal mass, which is physically impossible since the Sun is far too light to form one, Earth's orbit would be completely unchanged. The orbits of all the planets would continue exactly as before. What makes black holes extraordinary is not some enhanced gravitational reach, but the extreme density of the mass and what that creates near the event horizon. Out here, at orbital distances, a black hole is just another mass. The no-hair theorem, established in the 1960s and 70s through work by physicists, including Werner Israel, Brandon Carter, and David Robinson, states that a stationary black hole is completely described by exactly three numbers: its mass, its spin, and its electric charge. Astrophysical black holes formed from stellar collapse are electrically neutral in practice, leaving only mass and spin. All the complexity of the progenitor star, its chemical composition, its temperature, its magnetic fields, the history of its evolution, is entirely absent from the final black hole. The information carried by the infalling matter appears to be inaccessible from outside. Whether that information is truly destroyed or merely hidden is the central question of the black hole information paradox, one of the deepest unsolved problems in theoretical physics. Tidal forces near a black hole deserve special mention, because they are what make black holes lethal at distances well outside the event horizon. As you approach a black hole, the difference in gravitational pull between your head and your feet increases. Eventually, this difference is large enough to stretch you lengthwise and compress you laterally, a process physicists call spaghettification. For stellar mass black holes, this fatal tidal stretching begins thousands of kilometers from the event horizon. For supermassive black holes of 1 billion solar masses, the tidal forces at the horizon are gentle enough that you could cross the event horizon in apparent comfort before realizing that your destination is the singularity. The scale of the black hole changes the qualitative experience of falling into it completely. The term black hole itself was coined by American physicist John Archibald Wheeler in 1967 during a lecture at the NASA Goddard Institute. Before Wheeler's phrase took hold, these objects were awkwardly called gravitationally completely collapsed objects, or collapsed stars, or dark stars, a term John Michell had used in 1783 when he first theorized that gravity could trap light. Wheeler's two-word phrase was an act of scientific branding that changed how physicists talked about these objects and, in doing so, helped attract a generation of researchers to their study. Wheeler mentored Kip Thorne, one of the founders of LIGO. The connection from Michell's theoretical dark star to the detection of two of them colliding across 2 centuries of physics is one of the long arcs of the scientific story. The universe is not a place of isolated objects. More than half of all stars in the Milky Way are members of multiple systems. The fraction is even higher among the most massive stars, those above 15 solar masses, the ones that eventually become black holes. Studies suggest that more than 70% of these massive stars exist in binary or higher-order systems. The formation of a binary black hole therefore begins not with 2 lonely black holes finding each other in deep space, but with 2 massive stars that form together from the same cloud of gas and dust, bound by gravity from the moment of their birth. 2 massive stars in a close binary live an intimate and violent life together. Their mutual gravity distorts their shapes. Tidal forces transfer angular momentum. When the more massive star evolves and swells into a supergiant, it can overflow the region where its own gravity dominates and begin transferring mass to its companion. If this transfer becomes unstable, the expanding star's outer layers can engulf both stars in what is called a common envelope, a shared outer shell surrounding 2 orbiting cores. The cores spiral inward through the envelope, losing energy to friction, and if enough energy is deposited into that envelope, it gets ejected entirely. The 2 stripped stellar cores emerge in a much tighter orbit than before. The common envelope phase is one of the most uncertain stages in binary star evolution. The efficiency with which orbital energy is deposited into the envelope typically represented by a parameter called alpha, determines whether the binary survives. If too little energy is deposited, the cores spiral all the way in and merge prematurely as a pair of stellar cores rather than as black holes. If too much energy is deposited, the envelope is ejected easily, but the resulting orbit may be too wide to ever produce a merger within the age of the universe. The common envelope is a brief, violent event lasting perhaps a few thousand years in a stellar system that otherwise evolves over millions, yet it determines whether a binary black hole forms at all. The more massive core burns through its nuclear fuel first and undergoes core collapse. If the collapse produces a black hole, the first compact remnant is born. The explosion may be quiet. In some cases, the star collapses without a visible supernova, with most of its mass falling directly into the forming black hole. In other cases, a supernova does occur, and its asymmetry delivers a natal kick to the newly formed compact object. This kick can be hundreds of kilometers per second, and if it is large enough or poorly directed, it can completely unbind the binary, sending both objects flying away from each other forever. The survival of the binary through the first supernova is one of the central uncertainties in predicting how often binary black holes form. If the binary survives, the second massive star continues its own evolution. It too will exhaust its fuel, potentially undergo a second phase of mass transfer, and finally collapse. If both collapses produce black holes, and both times the system remains bound, the result is a binary black hole system. Two compact remnants in orbit around each other, separated by perhaps a few to tens of solar radii, with an orbital period of hours to days. This is the starting configuration for a merger. The road from here is irreversible. It may take billions of years, but the direction is set from the moment the binary black hole is born. A second important pathway involves globular clusters. Ancient, compact stellar systems containing hundreds of thousands to millions of stars packed into a region just tens of light years across. Black holes formed from massive stars in these clusters sink toward the center through dynamical friction and interact gravitationally with each other. These encounters can create bound binary black hole pairs through what is called gravitational capture or exchange interaction. Two previously unrelated black holes becoming gravitationally bound through a three-body or four-body encounter. This dynamical channel tends to produce mergers with more equal mass ratios and less spin alignment than the isolated binary channel. A third channel involves the dense gas disks around active galactic nuclei, the regions surrounding supermassive black holes at the centers of active galaxies. Stellar mass black holes wandering into these disks can be captured and embedded in the gas, which provides drag that circularizes their orbits and brings them into proximity with other embedded compact objects. The AGN disk channel may produce mergers with systematically different mass and spin properties than the isolated binary channel, giving gravitational wave astronomers a statistical tool for distinguishing formation histories across large samples of detected events. The metallicity of the progenitor stars, the abundance of elements heavier than helium in their composition, plays a critical role in determining the mass of the resulting black holes. Metal-rich stars drive stronger stellar winds and lose more mass during their lifetimes, arriving at core collapse with lighter remnant cores. Metal-poor stars, by contrast, retain more of their mass and can produce much heavier black holes. The heaviest black hole mergers detected by LIGO, involving objects of several tens of solar masses, almost certainly came from low metallicity progenitors. Stars formed early in the universe, or born in dwarf galaxies that have not been enriched through many generations of supernovae. An important observational clue about binary black hole formation comes from the mass gap. Theoretical models of stellar evolution predict that black holes should not form with masses between roughly 2 and 5 solar masses due to the physics of the core collapse and supernova explosion. Objects in this range are called lower mass gap objects. In August 2020, LIGO detected GW190814, a merger between a 23 solar mass black hole and an object of approximately 2.6 solar masses, placing the lighter component squarely in the mass gap. Whether that secondary was a particularly heavy neutron star or a particularly light black hole remains an open question. But the detection demonstrated that the mass distribution of compact binaries is richer and stranger than simple models. Predict population synthesis models attempt to predict the merger rate and mass distribution of binary black holes by simulating the full life cycle of millions of synthetic binary star systems. These models incorporate stellar evolution, mass transfer, supernova kicks, gravitational wave emission, and the various formation channels. They must be calibrated against the growing catalogue of LIGO detections. As of the third LIGO observing run, the observed merger rate is approximately 17 to 45 per cubic gigaparsec per year. A gigaparsec is approximately 3.3 billion light-years. The models broadly reproduce this rate, but significant uncertainties remain, particularly around common envelope evolution and supernova kick velocities. Every new gravitational wave detection refines these models. Once the binary black hole is formed, it is already doing something remarkable. It is radiating gravitational waves, not at the intensity of the final merger, that is still billions of years away, but at a slow, measurable rate that drains energy from the orbit and gradually draws the two black holes closer together. The orbit is shrinking. The merger is coming. It has been coming since the moment the second black hole was born. All that remains is time, and in the case of GW150914, approximately 1,300,000,000 years of it passed before the universe felt the result. The predicted gravitational wave merger rate, the number of binary black hole mergers per unit volume per unit time, was a key uncertainty before the first LIGO detections. Pre-detection theoretical estimates spanned roughly 6 orders of magnitude, from very optimistic to very pessimistic, reflecting how poorly constrained the formation physics was. The actual rate, now measured from the growing catalogue of LIGO events, is approximately 17 to 45 mergers per cubic gigaparsec per year. This rate is consistent with the middle of the pre-detection theoretical range, which was reassuring for the theorists who had built the models. The measured rate is now being used to calibrate the uncertain parameters in binary evolution codes, particularly the efficiency of common envelope ejection and the distribution of natal kick velocities from supernovae. Each new LIGO event narrows these parameters further. The inspiral phase of a binary black hole merger is by far the longest part of the story. It can last billions of years, and it follows from a single physical principle. Systems that radiate energy lose that energy from somewhere. In a gravitational system, the energy comes from the orbit. As the binary black hole radiates gravitational waves, it loses orbital energy. As it loses orbital energy, the orbit shrinks. The two black holes spiral inward, slowly at first, then faster as the shrinking orbit means stronger gravity and more emission, which means faster energy loss, which means faster shrinkage. The inspiral accelerates continuously, a feedback loop of growing intensity that culminates in the final moments of the merger. The mathematics of this process was worked out by physicist Peter Peters in 1964. His equations give the exact rate at which gravitational radiation carries energy and angular momentum away from a binary system, and from these, he derived how the orbit shrinks with time. The key result: the power radiated in gravitational waves is proportional to the square of the masses, and inversely proportional to the fourth power of the separation. Halving the separation increases the gravitational wave power by a factor of 16. The strongest emission comes when the two black holes are closest. The inspiral is self-reinforcing and irreversible. The combined mass and mass ratio of the binary determine the gravitational wave frequency at any given moment. But there is a particular combination of the two masses, called the chirp mass, that governs how quickly the frequency sweeps upward with time. The chirp mass is the quantity most precisely measured from the early inspiral part of the gravitational wave signal. For GW 150914, the chirp mass is approximately 28.3 solar masses. This single number, extracted from the shape of the signal, tells the physicist more about the system than any other quantity in the early inspiral, and was the first precise measurement extracted from the detection. For GW 150914, theoretical models suggest the binary may have been emitting gravitational waves at low frequencies for billions of years. In the early inspiral, with the two black holes perhaps tens of solar radii apart, the gravitational wave frequency would have been a tiny fraction of a hertz, completely undetectable by any instrument we have built. As the orbit slowly tightened over hundreds of millions of years, the frequency crept upward. Not until the final few seconds did the frequency enter the sensitive band of LIGO, sweeping through 10 Hz to 150 Hz in the last moments before merger. The eccentricity of the orbit, how elliptical it is compared to a perfect circle, also evolves during the inspiral. Gravitational wave emission preferentially damps eccentricity, tending to circularize orbits over time. By the time a binary system reaches LIGO's sensitive frequency band, most have circularized to very low eccentricity unless they formed recently through a dynamical encounter in a dense stellar cluster. In a dynamical encounter, the binary forms quickly and has not had time to circularize before entering the LIGO band. Measuring orbital eccentricity is therefore a potential signature of the formation channel, a measurable clue pointing toward the environment in which the binary was born. The spin-orbit coupling of the two black holes affects how the inspiral proceeds. If the spins of the black holes are tilted relative to the orbital angular momentum, the orbital plane precesses, it wobbles like a gyroscope. And this precession modulates the gravitational wave signal in a measurable way. For systems where the spins are randomly oriented, as expected from dynamical formation in a globular cluster, the precession effects are typically larger than for systems where the spins are aligned with the orbit, as expected from isolated binary evolution where tidal interactions tend to align the spin axes. Measuring spin precession from the gravitational wave signal provides statistical evidence about how the binary formed as the two black holes draw close, enough that their orbital velocities become a significant fraction of the speed of light. The analytical post-Newtonian approximation, which treats the orbital motion as a series of corrections to Newtonian gravity in increasing powers of the velocity divided by the speed of light, loses accuracy. This is the regime when numerical relativity becomes necessary. The first successful simulation of a complete binary black hole merger was published in 2005 by Franz Pretorius at Caltech, after decades of failed attempts. The key breakthrough was Pretorius's choice of a moving puncture coordinate system that allowed the numerical grid to follow the black holes without the coordinates becoming singular. The simulation ran on specialized supercomputers, and the result, a clean, accurate waveform from late inspiral through merger and ringdown, transformed the field overnight. The gravitational wave signal during the inspiral carries a detailed fingerprint of the system that produced it. By fitting a theoretical waveform template to the observed signal, physicists can measure the individual masses, the spins, the distance to the source, and the orientation of the orbital plane relative to Earth. This parameter estimation, using Bayesian statistical methods, is how the masses of 36 and 29 solar masses for GW 150914 were determined. The sky location, the luminosity distance of about 410 megaparsecs, and the inclination of the orbital plane all come from the same fit. The gravitational wave signal is, in a very literal sense, a self-contained data package containing a complete physical description of its source. LISA, the Laser Interferometer Space Antenna, is a planned European Space Agency mission consisting of 3 spacecraft separated by 2.5 million kilometers, flying in a triangular formation in heliocentric orbit, expected to launch in the mid-2030s. LISA will be sensitive to gravitational waves in the millihertz frequency band. In this band, binary black holes like the one that produced GW 150914 will be detectable years before their merger, while still in the early inspiral. LISA will track their frequency evolution, measure their chirp mass with extraordinary precision, and produce an advance alert for LIGO to be ready for the final seconds. For the first time, we will know a merger is coming before it arrives. The effective one-body formalism, developed by Alessandra Buonanno and Thibaut Damour in 1999, provides the mathematical bridge between the analytical post-Newtonian approximation used in the early inspiral and the numerical relativity solutions used during the final plunge and merger. The framework maps the two-body problem in general relativity onto an effective one-body problem, a single test particle moving in an effective curved spacetime, which can be solved analytically with corrections derived from numerical relativity simulations. The waveform models used for LIGO parameter estimation are built on the effective one-body framework, calibrated to large banks of numerical relativity runs. Without this mathematical machinery, extracting physical parameters from the measured gravitational wave signal would not be possible. It is invisible infrastructure, the engineering beneath the discovery. There is something profound about the long patience of the inspiral. Billions of years of orbital decay, each revolution nearly identical to the last, the separation decreasing by a fractional amount per orbit, the energy loss so gradual that no instrument built by any civilization could have measured it from a neighboring star, and yet it was happening, continuously. While the Earth formed, while the continents drifted, while evolution produced the first cells and then the first creatures capable of asking questions. All through that time, 2 black holes in a distant galaxy were circling each other, losing their orbital energy in ripples of space-time, drawing fractionally closer with each revolution, until the orbit could no longer hold, and they plunged. The merger of 2 black holes is over in milliseconds. After billions of years of slow inspiral, the final act is brutally brief. The 2 black holes, having passed inside the innermost stable circular orbit, accelerate toward each other in a final freefall that has no resemblance to the orderly orbital motion of the inspiral. Within fractions of a second, the 2 separate event horizons approach, distort, and merge into a single common event horizon. What was 2 objects becomes 1. From the outside universe, the merger is registered as the peak of the gravitational wave signal, the brief, bright maximum of amplitude that follows the long crescendo of the chirp. The newly merged object is not yet in its final state. It is what physicists call a distorted Kerr black hole. A Kerr black hole whose shape has been deformed away from the perfect mathematical form of the stationary solution. These deformations represent oscillation modes of the black hole, similar in concept to the vibration modes of a ringing bell. The distorted black hole oscillates, emitting gravitational waves with each oscillation, and the amplitude decays as energy is radiated away. This settling phase is called the ringdown, and it carries direct information about the mass and spin of the final merged object. The ringdown gravitational waves have a specific mathematical form, exponentially damped sinusoids, with frequencies and damping times determined entirely by the mass and spin of the final black hole. These are called quasi-normal modes. Their frequencies are among the most precisely predicted quantities in general relativity. The dominant quasi-normal mode for a black hole of approximately 60 solar masses, similar to the remnant of GW 150914, has a frequency of roughly 200 to 300 Hz and a damping time of a few milliseconds. Measuring the ringdown frequency and damping time and comparing them to the predicted values provides a direct test of whether the remnant behaves as general relativity predicts a Kerr black hole should. This test is called black hole spectroscopy. The energy released during the merger is staggering. For GW 150914, the total gravitational wave energy radiated was approximately 3 solar masses times the speed of light squared, about 5.3 times 10 to the power of 47 joules. The peak gravitational wave luminosity in the final milliseconds was approximately 3.6 times 10 to the power of 49 watts. The luminosity of the Sun is about 3.8 times 10 to the power of 26 watts. The peak gravitational wave power was roughly 10 to the power of 23 times the Sun's luminosity, greater than the combined electromagnetic output of every star in the observable universe, concentrated into a fraction of a second. The source of this energy is purely gravitational. When two massive objects are in highly dynamic configurations, they radiate gravitational waves because they have a changing quadrupole moment, a measure of how non-spherical their combined mass distribution is. Two black holes in their final orbit are changing shape continuously at extreme speed, producing maximum gravitational wave power. After the ringdown, the merged black hole is a stationary Kerr object, time-independent in shape, and gravitational wave emission ceases entirely. The energy that was in the orbit is now dispersed across billions of light-years of spacetime as a passing wave. Nothing was burned, fused, or exploded. The energy was entirely in the geometry. There is a dramatic secondary consequence of the merger: gravitational recoil, or the black hole kick. Gravitational waves carry not only energy but also momentum. If the emission during the merger is not perfectly symmetric, which it generally is not, particularly when the merging black holes have unequal masses or misaligned spins, the system radiates more gravitational wave momentum in one direction than the other. By conservation of momentum, the merged black hole recoils in the opposite direction. This kick can be hundreds of kilometers per second for typical mergers, and in special spin configurations, called superkick configurations, can reach tens of thousands of kilometers per second. The escape velocity from a globular cluster is only a few tens of kilometers per second. Most merged black holes receive a gravitational wave kick large enough to eject them from their host cluster entirely. This has important implications for the hierarchical merger scenario discussed in Chapter 8. A black hole ejected from its cluster cannot immediately participate in another merger in that environment. Instead, it wanders through its host galaxy alone, potentially being captured by a different dense stellar system over time, or simply remaining isolated indefinitely. The kick velocity distribution depends on the mass ratio and spin properties of the merging pair, making it another statistical, observable connecting gravitational wave data to astrophysical environments. A phenomenon called the gravitational wave memory effect deserves mention. During a merger, the gravitational wave signal contains not only the oscillatory part, the chirp and ringdown, but also a non-oscillatory component called the displacement memory. As the gravitational waves pass through a region of space, they leave behind a permanent, non-oscillating deformation. Two free masses exposed to the memory effect will end up slightly farther apart, or closer together, than they were before the wave passed, and they will not spring back. This permanent offset is too small for current detectors to observe directly, but it is a clear prediction of general relativity, and future space-based detectors should be able to detect it in the signals from the most massive mergers. The final merged black hole is a Kerr black hole characterized by exactly two numbers, its mass and its spin. All other properties of the progenitor system, the individual masses, the orbital parameters, the history of the inspiral, are encoded only in the gravitational waves that have already departed. The black hole itself retains none of this history. This is the no-hair theorem in its most dramatic form. 1 billion years of stellar evolution and orbital mechanics reduced, in an instant, to two numbers. The richness of the story that produced the black hole leaves no fingerprint on the object itself. All the information went into the ripples. Hawking's area theorem, proved in 1971, states that in classical general relativity, the total surface area of black hole event horizons can never decrease. In a merger, the final black hole's event horizon area must be greater than the sum of the two original areas. For GW 150914, the numbers confirm this, even accounting for 3 solar masses radiated away. The area of the 62 solar mass remnants horizon exceeds the combined area of the progenitors. The merger is irreversible, thermodynamically final. The area theorem is the black hole equivalent of the second law of thermodynamics, and the merger is its most dramatic macroscopic demonstration in the universe. Black hole spectroscopy, the program of measuring multiple quasi-normal mode frequencies from the ring-down signal of a merged black hole, is emerging as one of the most powerful tests of general relativity available to gravitational wave astronomy. General relativity predicts that all the quasi-normal mode frequencies and damping times of a Kerr black hole are uniquely determined by just two numbers, the mass and spin. If the ring-down signal contains two independently measurable modes, and if those two modes are consistent with the same mass and spin, it confirms that the merger product is a Kerr black hole as described by general relativity. Any deviation would be evidence for new physics beyond general relativity, modifications to gravity, or exotic compact objects mimicking black holes. Current detectors can barely resolve the dominant mode in the strongest events. Third-generation detectors will perform full spectroscopy routinely, subjecting general relativity to its most rigorous experimental test ever conducted. Gravitational waves were predicted by Albert Einstein in 1916, the same year Carl Schwarzschild worked out black hole geometry. In his general theory of relativity, Einstein showed that accelerating masses produce disturbances in the spacetime metric, and that these disturbances propagate outward at the speed of light. The prediction followed directly from the mathematics. But Einstein himself was uncertain for many years whether gravitational waves were physically real, or merely a mathematical artifact of the coordinate system used to describe the theory. The debate was not resolved until the 1950s, when Hermann Bondi and Richard Feynman demonstrated independently that gravitational waves carry real energy and can do work on a mechanical detector. A gravitational wave is a distortion of the spacetime metric itself that propagates at the speed of light. Unlike electromagnetic waves, which are disturbances in the electromagnetic field, gravitational waves are disturbances in the very geometry of spacetime, through which all matter and fields exist. This makes them fundamentally different in one crucial respect. An electromagnetic wave can be blocked by sufficiently dense material. A gravitational wave is not blocked by matter because it is a distortion of the space-time that matter inhabits. It passes through everything, including planets and stars, with essentially no absorption. Earth is completely transparent to gravitational waves. A wave from a black hole merger, 1 billion light years, a wave passes through the entire planet as if it were not there. Gravitational waves come in two polarizations, called the plus polarization and the cross polarization. The plus polarization stretches space in one direction while compressing it in the perpendicular direction, then reverses, alternating at the wave frequency. The cross polarization does the same but rotated by 45 degrees. A binary black hole merger produces a superposition of both polarizations with relative amplitudes and phases that depend on the orientation of the orbital plane relative to the observer. When the orbital plane is face onto the observer, the two polarizations are equal in amplitude. When the orbital plane is edge-on, only one polarization is present. Measuring both polarizations independently requires at least two well-separated detectors. The effect of a passing gravitational wave is characterized by the strain, denoted h, the fractional change in length the wave produces in any measuring rod. For GW 150914, the strain at Earth was approximately 10 to the power of -21. LIGO's 4-kilometer arms were stretched and squeezed by about 4 times 10 to the power of -18 meters, roughly 1,000th of the diameter of a proton. This is why gravitational wave detection is described as one of the most precise measurements ever made. The strain is so small because gravity is the weakest of the fundamental forces, and even two black holes of 30 solar masses colliding at near the speed of light can only manage a strain this faint across 1 billion light years. Gravitational waves travel at exactly the speed of light. This was directly confirmed by the binary neutron star merger GW 170817, observed in August 2017. That event produced both a gravitational wave signal and a short gamma-ray burst detected by orbiting telescopes. The two signals had been traveling for approximately 130 million years and arrived at Earth within about 1.7 seconds of each other. This constrains the speed of gravitational waves to within 15 parts per 1,000 billion of the speed of light, a precise confirmation of a 100-year-old prediction. The binary neutron star merger was also the first multi-messenger gravitational wave event. After the gravitational wave alert, over 70 observatories worldwide pointed at the source location and detected the electromagnetic afterglow at radio, optical, infrared, X-ray, and ultraviolet wavelengths over the following days and weeks. This multi-messenger observation confirmed neutron star mergers as a major site of heavy element production, including gold, platinum, and uranium, and enabled an independent measurement of the Hubble constant. Multi-messenger astronomy, combining gravitational waves with light, is now one of the most productive frontiers in astrophysics. Gravitational waves also carry information about cosmology in a unique way. The gravitational wave signal from a binary merger encodes the luminosity distance to the source, the actual distance, without requiring calibration against any other standard. This makes gravitational wave sources what cosmologists call standard sirens, self-calibrating distance probes. As LIGO accumulates more detections, the statistical combination of many standard siren distance measurements will yield an increasingly precise independent measurement of the Hubble constant, potentially resolving a long-standing tension between the values measured by different conventional methods. Each new detection is a vote in this measurement. Universe may contain a stochastic gravitational wave background, produced by the superposition of all unresolved binary black hole mergers throughout the history of the cosmos. Just as the cosmic microwave background is the sum of all photons released at the epoch of recombination, this gravitational wave background would be the sum of all gravitational waves from compact binary mergers across all of cosmic time. The background is expected to be detectable with future sensitivity upgrades to the LIGO network. Its amplitude and spectral shape would encode the merger rate history of the universe, a new archaeological record of structure formation written in spacetime itself. Primordial gravitational waves from the epoch of cosmic inflation, the period of exponential expansion in the first fraction of a second after the Big Bang, represent yet another potential source. Inflation is predicted to produce a background of tensor perturbations, gravitational waves, that would imprint a specific pattern called B-mode polarization on the cosmic microwave background. Detecting this signature would be direct observational evidence for inflation. Several experiments, including the BICEP and Keck telescope programs at the South Pole, are searching for this signal. Its detection would open a gravitational wave window onto the earliest moment in the history of the universe. Advanced quantum optical techniques have pushed the sensitivity of the LIGO detectors closer to the fundamental quantum noise limits. One of these is quantum squeezing, a technique that uses the quantum correlations of entangled photon pairs to reduce the noise in the phase measurement of the laser at the cost of increased noise in the amplitude measurement that is less relevant to gravitational wave detection. Squeezed light injection was installed in the LIGO detectors during the third observing run and has since been routinely used, extending the sensitivity in the shot noise limited frequency range above approximately 50 Hz. This improvement directly increases the detection rate of binary black hole mergers and improves the quality of parameter estimation for each event. The intersection of quantum optics and gravitational wave astronomy is one of the more surprising frontiers in experimental physics. The universe has been broadcasting gravitational waves since the first massive binary star systems merged, billions of years before we had instruments to hear them. Every black hole collision in the history of the cosmos sent its ripple outward through space-time. Most of those ripples passed our location long ago and are now billions of light years beyond us. Some are arriving right now from mergers in distant galaxies. The universe speaks in gravitational waves continuously. The story of how we built machines sensitive enough to detect that speech. Machines that can measure a change smaller than a proton across a 4-kilometer arm is one of the great achievements of experimental physics. That story is the subject of the next chapter. The theoretical case for detecting gravitational waves using a laser interferometer was laid out in a 1972 technical report by Rainer Weiss of the Massachusetts Institute of Technology. Weiss showed in careful detail how a Michelson interferometer, a device that splits a laser beam into two perpendicular arms, reflects it back from mirrors, and recombines the beams to detect path length differences through interference, could detect gravitational waves if the arm length was long enough and noise was sufficiently controlled. His report identified the main noise sources: seismic vibrations, thermal motion of mirror surfaces, and quantum noise in the photon measurement. It was, in effect, a complete roadmap for building LIGO, written over 40 years before the first detection. Kip Thorne at the California Institute of Technology became convinced in the late 1970s that gravitational wave detection was both achievable and scientifically transformative. He collaborated with Weiss to develop the scientific case and recruited colleagues at Caltech and MIT to begin experimental work. Barry Barish joined the project in 1994 at a critical moment. The project had funding, but was behind schedule and at risk of cancellation. Barish, a particle physicist with experience managing large international collaborations, reorganized LIGO into a scientifically rigorous enterprise and built it into a global collaboration of over 1,000 scientists. The Nobel Committee recognized all three by awarding Weiss, Barish, and Thorne the Nobel Prize in Physics in 2017. Each LIGO detector is an L-shaped vacuum chamber with arms 4 kilometers long. Inside each arm, a laser beam travels between two suspended mirrors, polished glass discs each weighing 40 kilograms, hanging on a 4-stage pendulum system designed to isolate them from seismic vibrations. The beam bounces between the mirrors approximately 280 times before recombination, giving an effective optical path length of about 1,100 kilometers per arm. When a gravitational wave passes through, it changes the length of one arm relative to the other by an amount proportional to the strain. This differential length change alters the interference pattern at the output photodetector, producing the signal. The detectors are limited by different noise sources in different frequency ranges. Below about 10 Hz, seismic noise dominates. Ground vibrations from ocean waves couple into the mirrors despite the isolation systems. At intermediate frequencies, thermal noise in the mirror coatings is a major limitation. The random motion of atoms at room temperature produces small fluctuations in the mirror surface. Above about 200 Hz, quantum shot noise, the statistical randomness in photon counting, becomes dominant. Advanced LIGO, which completed commissioning in late 2015, incorporated upgrades to reduce all three noise sources, increasing sensitivity by a factor of 3 to 4 over the original LIGO detectors. On the morning of September 14th, 2015, Marco Drago's alert arrived during a commissioning phase of the first advanced LIGO observing run. The signal-to-noise ratio in the matched filter analysis was approximately 24, against a detection threshold of 8. A signal-to-noise ratio of 24 is exceptional. Most detections since have been in the range of 8 to 15. The estimated false alarm rate was less than 1 event per 200,000 years. 5 months of analysis followed. The signal arrived in Livingston 7 milliseconds before Hanford, consistent with the expected travel time difference for a gravitational wave arriving from the southern sky. Every test passed. On February 11, 2016, physicist David Reitzer opened the announcement press conference with the words, "We have detected gravitational waves." We did it! The room erupted. For scientists who had spent their careers on this project, some since the 1980s, the emotion was visible and genuine. In scientific terms, the announcement was the confirmation of a 100-year-old prediction of general relativity, the first direct detection of a binary black hole system, and the opening of an entirely new observational window on the universe. All three simultaneously in one signal. Detections accumulated quickly after the announcement. The third gravitational wave transient catalogue, covering observations through March 2020, contains over 90 confirmed events. Most are binary black hole mergers, spanning a wide range of masses. GW 190521 stands out for producing a merged remnant of approximately 150 solar masses in the intermediate mass black hole range. GW190814 was the unequal mass event where the secondary was likely in the mass gap between neutron stars and black holes. Each new event adds to a statistical picture of the mass and spin distribution of compact binary populations across the universe. The Virgo detector near Pisa, Italy, joined the observing network in August 2017, and the Kagra detector in Japan began operations in 2020. With detectors on multiple continents, the network can now localize gravitational wave sources on the sky to tens of square degrees in the best cases, enabling rapid electromagnetic follow-up. The more detectors operating simultaneously, the better the sky localization, and the more polarization information is available. The global network is essential for extracting the full scientific content of each event. The future of ground-based gravitational wave detection is an upgrade to so-called third-generation detectors. The Einstein telescope, a proposed European underground triangular detector with 10-kilometer arms, and Cosmic Explorer, a proposed American detector with arms up to 40 kilometers, would be sensitive to binary black hole mergers throughout the entire observable universe, with a detection rate potentially of thousands per year. At that rate, gravitational wave astronomy shifts from individual event science to population science. The statistical study of the mass, spin, and redshift distribution of all merging compact objects in the universe. The full census of black hole mergers from the first stars to today within reach. The gravitational wave sky is richer and stranger than the pre-detection models predicted. Several events in the current catalogue are difficult to explain with standard formation channels. GW190521, with a total mass of approximately 150 solar masses, suggests at least one hierarchical merger product. GW210521, detected in the fourth observing run, appears to involve a black hole of unusually high spin. The event GW190425 has a secondary mass possibly in the neutron star range, making it potentially a black hole neutron star merger, rather than a binary black hole system. Each anomalous event is a clue about a formation pathway, a stellar evolution outcome, or a compact object class that standard models did not fully anticipate. The catalogue is teaching us things that no amount of theoretical work could have revealed in advance. A significant challenge in gravitational wave data analysis is distinguishing genuine astrophysical signals from instrumental artifacts called glitches. These transient noise events can resemble gravitational wave signals in duration and frequency content, and are caused by a wide variety of environmental and instrumental disturbances. The LIGO collaboration maintains continuous environmental monitoring with hundreds of auxiliary sensors at each site, measuring everything from seismic ground motion and acoustic noise to magnetic fields and cosmic rays. Automated glitch classification algorithms, including machine learning systems trained on thousands of labeled examples, flag anomalous noise events in near real time. Human citizen scientists also participate through a project called Gravity Spy, classifying glitches displayed as time-frequency images on a web platform. The result is a highly characterized data stream in which genuine gravitational wave signals can be identified with confidence against a well-understood noise. Background. What Weiss described in a technical report in 1972, Barish organized into a functioning scientific institution, and Thorne championed as the most important astrophysics experiment of the century, now detects black hole mergers multiple times per month during observing runs. The machine that measures 1,000th of a proton diameter across 4 kilometers, that extracts the masses and spins of black holes from 0.2 seconds of data, that has opened a sense humanity never had before. That machine is running right now. The detectors are listening. The black holes detected by LIGO are stellar mass objects, from a handful to a few hundred solar masses. But the universe also contains black holes on an entirely different scale. The supermassive black holes at the centers of virtually all large galaxies, ranging from about 1 million to many tens of billions of solar masses. These objects did not form from individual stellar deaths. They grew over billions of years through combinations of gas accretion and mergers with other massive black holes. When two of them merge, the event is incomparably more energetic than anything in the stellar mass regime, and the gravitational waves produced are at such low frequencies that no ground-based instrument can detect them. The supermassive black hole at the center of our own Milky Way is called Sagittarius, a star. Its mass is approximately 4 million solar masses, compressed into a region smaller than the orbit of Mercury. Its existence was confirmed through decades of tracking the orbits of stars near the galactic center using infrared telescopes. The star known as S2, for instance, completes an orbit of the central black hole in approximately 16 years, with a closest approach of about 120 astronomical units. The orbital parameters determine the central mass with high precision. This work, led by teams under Reinhard Genzel and Andrea Ghez, earned them the Nobel Prize in Physics in 2020. When two galaxies merge, as the Milky Way and the Andromeda Galaxy are expected to do in approximately 4 to 5 billion years, their central supermassive black holes do not immediately merge. The galaxy merger is a gravitational process taking hundreds of millions of years. The two supermassive black holes, initially separated by tens of thousands of light years, sink toward the center of the merged galaxy through dynamical friction. As each black hole moves through the surrounding stellar mass, it scatters stars gravitationally, losing orbital energy in the process. Eventually, they form a gravitationally bound binary pair, orbiting each other at separations of a few light years. Closing the final separation to produce an actual merger is more difficult. Once the binary is tight enough that it has scattered away most nearby stars, the supply of stars for further dynamical friction begins to run out. This is the final parsec problem. In a perfectly spherical, smooth stellar distribution, the two supermassive black holes can approach to within roughly 1 parsec, but then stall, starved of further energy loss mechanisms. In practice, non-spherical galaxy potentials, gas dynamics, and further minor galaxy mergers can all provide the necessary angular momentum removal to bridge the final parsec. Observational evidence for supermassive black hole binaries at subparsec separations implies that nature resolves this problem, even if the precise mechanism is uncertain. The candidate binary supermassive black hole system OJ287 is among the most studied examples. Located about 3.5 billion light-years away, its optical brightness has been monitored for over 120 years, making it one of the longest baseline photometric records in astrophysics. The light curve shows quasi-periodic oscillations with outburst pairs repeating on a roughly 12-year cycle. The most widely accepted model invokes a primary black hole of approximately 18 billion solar masses and a secondary of about 150 million solar masses in a precessing eccentric orbit. The secondary punches through the primary's accretion disk twice per orbit, producing a thermal outburst each time. This system is a living laboratory for supermassive binary dynamics. The gravitational waves produced by supermassive black hole binaries have frequencies far below the LIGO band. A binary with two black holes of 1 billion solar masses each and an orbital period of 1 year emits gravitational waves at about 30 nanohertz, 30 billionths of a hertz. Detecting these requires pulsar timing arrays. Millisecond pulsars are rapidly rotating neutron stars that emit pulses of radio waves with a stability rivaling atomic clocks. A gravitational wave passing between Earth and a pulsar slightly changes the effective distance, advancing or delaying the arrival of pulses by a tiny but measurable amount. By monitoring many pulsars simultaneously and looking for correlated timing deviations with the characteristic quadrupolar pattern expected from a gravitational wave background, pulsar timing arrays detect the accumulated signal. In June 2023, the North American Nanohertz Observatory for Gravitational Waves announced evidence for a gravitational wave background at nanohertz frequencies, based on 15 years of monitoring data from 67 millisecond pulsars. Simultaneous findings from European, Indian, and Australian pulsar timing array collaborations confirmed the result. The characteristic signature of the background, a specific pattern of correlations between different pulsars as a function of their angular separation on the sky, called the Hellings-Downs correlation, was detected for the first time. This correlation is the definitive fingerprint of a gravitational wave background as distinct from other sources of correlated noise. Its amplitude and spectral slope are consistent with the cosmic population of supermassive black hole binaries. The Laser Interferometer Space Antenna, LISA, is designed to detect gravitational waves from massive black hole mergers, black holes in the range of 10,000 to 10 million solar masses, across the entire observable universe. A merger of two black holes of 1 million solar masses each would produce a signal in LISA detectable from any galaxy in the observable universe, with a signal-to-noise ratio of hundreds or thousands. LISA will detect these events with months of advance warning during the inspiral, providing precise sky localizations for electromagnetic observatories to pre-point and observe the merger environment simultaneously. The first direct observation of a massive black hole merger beginning to end is a central scientific goal of the LISA mission. The direct image of Messier 87 star, the supermassive black hole at the center of the Messier 87 galaxy, released by the Event Horizon Telescope in 2019, showed a bright asymmetric ring of emission surrounding a dark central shadow. The ring results from photons bent into near-circular orbits around the event horizon, with the asymmetry arising because the near side of the accretion disk is Doppler boosted toward the observer. The diameter of the shadow matched the prediction of general relativity for a black hole of 6.5 billion solar masses to within the measurement uncertainties. A second image was released in 2024 showing the magnetic field structure near the event horizon, tracing the ordered large-scale field that is thought to power the relativistic jet extending thousands of light years from the galaxy's nucleus. Very long baseline interferometry observations at radio wavelengths have begun to resolve the immediate environments of candidate supermassive black hole binary systems. By combining signals from radio telescopes separated by thousands of kilometers, or using space-based radio telescopes, by the diameter of Earth's orbit, these observations can achieve angular resolutions of microarc seconds, sufficient to resolve structures on scales of light years around distant galactic nuclei, searching for binary orbital motion on timescales of years or decades in these compact radio cores is one of the observational strategies for identifying supermassive black hole binaries before the gravitational wave signal from their final merger becomes detectable. The radio, optical, pulsar timing, and eventual gravitational wave observations of these systems will all be needed together to understand the full physics of their evolution. The full landscape of gravitational wave astronomy now spans an enormous range of frequencies and source types. At the LIGO end, stellar mass binary black holes and neutron star mergers complete their final orbits in seconds, and are detected individually. At the LISA end, mergers of massive black holes in dwarf galaxy nuclei will be visible across the observable universe. And at the nanohertz end, now accessible to pulsar timing arrays, the stochastic background from the accumulated history of all supermassive black hole mergers throughout cosmic time hums continuously. The universe is a gravitational wave observatory at every frequency, all the time. The question has always been whether we could listen. Every black hole merger that has ever occurred in the history of the universe has left behind a larger black hole. The merged object is more massive than either progenitor by the amount not radiated away as gravitational waves. The universe is not a place where black holes are consumed in their collisions. It is a place where they are combined and enlarged. Over billions of years, since the first massive stars died and the first black holes were born, this accumulation has been ongoing. The cumulative result is a universe in which black holes, once rare endpoints of stellar evolution, have become the dominant form of collapsed matter over cosmological timescales. Hierarchical black hole growth, smaller objects merging to form larger ones, which merge again, is one explanation for supermassive black holes. The most massive known black holes, weighing tens of billions of solar masses, cannot have accreted all of that mass from gas alone in the available time. There is a maximum rate at which a black hole can accrete without the radiation pressure of the accreting gas pushing material away, called the Eddington limit. Accreting continuously at this limit from the Big Bang to today is insufficient to explain the most extreme masses. Mergers between massive black holes during galaxy collisions are a necessary complement to gas accretion in accounting. For the heaviest supermassive black holes, the detection of GW190521 in 2000 and 20 provided one of the most striking examples of hierarchical growth. The merged object had a mass of approximately 140 to 160 solar masses, well within what stellar evolution theory calls the pair instability mass gap, a range where individual stellar core collapse is predicted not to produce a black hole directly. The most likely explanation is that one or both of the progenitor black holes were themselves the products of previous black hole mergers, their masses accumulated through hierarchical collisions in a dense stellar environment. Each generation of mergers produces heavier remnants, building upward toward intermediate mass black holes of hundreds or thousands of solar masses. To understand what happens over truly long timescales, we consider the degenerate era, the period beginning roughly 10 to the power of 40 years from now, when the last stars have burned out. The universe will then be populated primarily by white dwarfs, neutron stars, and black holes, along with the remnants of planetary systems orbiting the cooling husks of dead stars. Active star formation will have ended, the light of living stars will be gone. What remains is the slow cooling and dissipation of the structures built during the stellar era, playing out over timescales that make the current age of the universe seem brief. The most important long-term process for black holes is Hawking radiation. In 1974, Stephen Hawking applied quantum field theory to the geometry near a black hole event horizon and derived a result that surprised almost everyone in theoretical physics. Black holes are not perfectly black. They radiate thermally, with a temperature inversely proportional to their mass. The radiation arises from quantum effects near the horizon. The black hole's gravitational field produces particle pairs from the quantum vacuum, with one particle escaping to infinity, while the other effectively falls in and reduces the black hole's mass. Over time, the black hole loses mass and eventually evaporates completely. The Hawking temperature of a stellar mass black hole of 10 solar masses is approximately 6 times 10 to the power of -9 Kelvin, a fraction of a billionth of a degree above absolute zero. In the current universe, this is far colder than the 2.7 Kelvin cosmic microwave background, meaning stellar mass black holes are absorbing more radiation from the CMB than they emit via Hawking radiation. They are currently gaining mass from their environment, not losing it. Only when the universe has expanded and cooled sufficiently, in roughly 10 to the power of 23 years, will stellar mass black holes begin to net evaporate. The evaporation timescale for a stellar mass black hole is approximately 2 times 10 to the power of 70 years. The black hole information paradox asks what happens to information about the quantum state of matter that falls into a black hole and is then radiated away by Hawking evaporation. General relativity suggests the information is destroyed. The no-hair theorem says the black hole retains no record of what fell in, and Hawking's original calculation suggested the outgoing radiation is purely thermal and carries no information. But quantum mechanics forbids the destruction of information. It must be preserved somewhere. The tension between these two principles is one of the deepest unresolved problems in theoretical physics. Recent work by Geoffrey Pennington and Ahmed Almhiri, Netta Engelhardt, Henry Maxfield, and Jeff Pennington has suggested through calculations involving the so-called page curve that information is indeed preserved, escaping in subtle quantum correlations within the Hawking radiation. The mechanism remains under active investigation. As a black hole evaporates and its mass decreases, its Hawking temperature rises. The evaporation accelerates. In the final moments, when the mass has been reduced to roughly the Planck mass, about 22 micrograms, the temperature spikes and the black hole completes its evaporation in a brief burst of high-energy particles. In the cold, dark universe of the black hole era, this final burst from a single evaporating stellar mass black hole would be the most energetic event in the observable universe at that time. The burst lasts about 10 to the power of -43 seconds. Then the silence returns. Black hole thermodynamics, the formal analogy between the laws of black hole mechanics and the laws of thermodynamics, is one of the most productive frameworks in theoretical physics. The area theorem corresponds to the second law. The surface gravity of the event horizon corresponds to temperature. The black hole mass corresponds to energy. These are not mere analogies. Hawking's calculation of black hole temperature gave them physical reality. The Bacon-Stein-Hawking entropy formula, expressing the entropy of a black hole as proportional to the area of its event horizon, is one of the few results that combines general relativity, quantum mechanics, and thermodynamics in a single equation. Understanding its microscopic origin, what physical degrees of freedom account for the entropy, is one of the central goals of quantum gravity research. The Bacon-Stein-Hawking entropy formula states that the entropy of a black hole is proportional to the area of its event horizon, measured in units of the Planck area, approximately 10 to the power of -70 square meters, for a stellar mass black hole of 10 solar masses. This entropy is approximately 10 to the power of 78 in natural units, incomparably larger than the entropy of the star that formed it, or of any ordinary thermodynamic system of comparable mass. The enormous entropy of black holes is one of the deepest puzzles in theoretical physics. It implies that black holes are the most efficient entropy-generating objects in the universe. Understanding what physical degrees of freedom, what microscopic configurations, correspond to this entropy requires a complete theory of quantum gravity. String theory and loop quantum gravity each offer partial answers, but the complete microscopic accounting of black hole Entropy remains one of the central unsolved problems at the intersection of quantum mechanics and general relativity. What comes after all? Black holes have evaporated. The universe would contain primarily photons, neutrinos, and the lightest stable particles at densities so low that any physical interaction would be extraordinarily rare. No stars, no chemistry, no biology, no structure of any kind requiring an energy gradient to exist. The universe ends not in explosion but in stillness. And the gravitational waves from all the mergers that ever happened, from the first black holes that formed to the last ones that evaporated, are still traveling through that stillness, weakened almost beyond measure but present, still carrying their message, still moving at the speed of light through a universe that has otherwise gone quiet. On the morning of September 14th, 2015, before Marco Drago's alert arrived, before anyone in the LIGO collaboration had any idea what was about to be found, the universe had already been broadcasting for 1,300,000,000 years. The ripple from that black hole collision had been traveling since before the Earth formed. It had passed through our galaxy hundreds of millions of years before there were any creatures here capable of detecting it. And then it finally reached two instruments sensitive enough to register its passage. 1,300,000,000 years of travel. 0.2 seconds in the detector. Those numbers do not fully communicate what that means, but they try. Before that morning, we had studied the universe through light, electromagnetic radiation in every wavelength, visible light, radio waves, X-rays, gamma rays, produced by matter and energy interacting through the electromagnetic force. This light told us about temperatures, compositions, and velocities. It told us about stellar lifetimes and galaxy formation and the large-scale structure of the cosmos. But it was completely silent on one specific class of event. Two black holes merging, both electromagnetically dark by definition, leaving no light any telescope could detect. Until 2015, these events were invisible to us. They existed in the universe. We had no way of knowing. After that morning, we had a new sense. Gravitational wave astronomy is not merely a new branch of electromagnetic astronomy. It is a genuinely new way of perceiving the universe, using a fundamentally different physical phenomenon, where electromagnetic astronomy sees the universe through light. Gravitational wave astronomy feels the universe through distortions of space itself. The two approaches are complementary in the way that hearing and sight are complementary. Each reveals aspects of reality that the other cannot. Multi-messenger astronomy combining both has already transformed our understanding of neutron star mergers, heavy element synthesis, and cosmological expansion. And it is young. The catalogue is still small. The science is in its opening chapters. The future detections that are coming will be extraordinary. Third-generation detectors will hear binary black hole mergers from the very first stars in the universe, the so-called population 3 stars, that formed from nearly pure hydrogen and helium in the first 100 million years. We will detect the black holes those stars left behind, merging with each other across billions of years. We will reconstruct the merger history of black holes from the cosmic dawn to the present day, and the picture of how structure formed in the universe will become richer and more detailed than anything we can currently imagine. We will also search for unexpected sources, cosmic strings, first-order phase transitions in the early universe, boson clouds forming around rapidly spinning black holes through quantum processes. The universe has surprises prepared for the detectors we are building. The scientific literature describes the sensitivity of LIGO using the concept of the binary neutron star range, the distance at which LIGO can detect the merger of two standard 1.4 solar mass neutron stars with a signal-to-noise ratio of 8. During the first advanced LIGO observing run, this range was approximately 60 to 80 megaparsecs. By the fourth observing run, Ongoing improvements had pushed it beyond 160 megaparsecs for the Livingston detector. Each improvement in range corresponds to a cube of volume. Doubling the range increases the detectable volume by a factor of 8 and the expected event rate accordingly. The drive to increase the binary neutron star range and the corresponding range for heavier black hole systems is what motivates every engineering upgrade to the detector, from mirror polishing to quantum squeezing to seismic isolation improvements. There is a particular quality to LIGO's sensitivity that I find worth dwelling on. The detectors are so sensitive that they respond to disturbances from distant coastal waves. Seismic noise from the Pacific Ocean reaches the Livingston detector. The gravitational pull of passing vehicles on roads near the facility is detectable in the data. The instrument is so exquisitely tuned to feel the fabric of space-time that it feels everything. And yet within all that noise, within the constant trembling of Earth, the thermal motion of the mirrors, the quantum uncertainty of the photon counts, the signal from two black holes a billion light-years away emerges cleanly, unmistakably, with a signal-to-noise ratio of 24. The achievement of that sensitivity is, in its own way, as remarkable as the discovery itself. What moves me most about GW150914 is not the physics, extraordinary as it is. It is the patience. Two black holes circling each other for billions of years, losing energy in ripples so faint that nothing could detect them from outside the solar system. The universe does not hurry. Two massive remnants under the influence of gravity followed the mathematics of general relativity exactly, without exception, without deviation, across more time than the Earth has existed. And eventually, the mathematics brought them together. It always does. The merger is not an event in the way we usually think of events. Something witnessed, recorded, celebrated. It is simply physics running to its inevitable conclusion. And yet we were there. Not physically. We were a billion light-years away, and the event had already happened long before our planet formed. But we were there in the sense that matters for a species capable of science. We built instruments sensitive enough to register the ripple when it arrived. We interpreted that ripple correctly. We translated 0.2 seconds of data into a picture of two black holes completing their final orbit in a distant galaxy a billion years ago. We reconstructed the masses, the spins, the distance, the orientation. From almost nothing. The capacity of science to extract meaning from physical signals, at the limit of what instruments can measure, is one of the most extraordinary things that has ever happened on this small planet. There is something particularly appropriate about watching content like this before sleep. The scale of these events, billions of years, billions of light years, solar masses by the tens, has a quality that releases ordinary human concerns. The merger of two black holes does not care about tomorrow's obligations or the events of the day that just ended. The universe preceded us by 13.8 billion years. It will continue long after the last star burns out. In that context, the brief period of human wakefulness that filled your day is a flash of light, vivid and complete and sufficient. Sleep is the time when that perspective settles in. The universe is very large. You are allowed to rest. Two black holes found each other. They danced for a billion years. They merged in a fraction of a second. The gravitational waves from that merger have now traveled 14 million light-years beyond Earth. They are out there right now, heading toward galaxies we have never seen and will never see, carrying the record of that collision through an expanding universe. They will continue to travel long after the sun has expanded, long after the Earth has gone quiet, long after every instrument we have ever built has dissolved. The universe will carry that record outward for as long as the space-time geometry allows, which, by all current physics, is effectively forever. We were here when the message arrived. We read it, we understood it. In the vast, indifferent story of the cosmos, that is not nothing. That is the closest thing to something that a small warm-blooded creature on a small rocky planet has ever achieved. You are here. The universe is immense and old and full of events you will never witness. But tonight you heard the story of one of them. Let the scale of it settle. Let the wonder outlast the wakefulness. Sleep well.